I will talk about a work that we have carried out in a collaboration with IMT Lille with Cedric Samuel in the frame of a joint PhD degree with Alexander Neff about the processing of PVDF films by melt-state extrusion in order to investigate the impact of the PMMA on the beta phase crystallization, particularly responsible for the piezoelectricity properties of PVDF films. Piezoelectric polymers are part of the smart matters, so matters having the ability to respond to any external stimuli like temperature. We have different examples based on the self-healing effect, such as the matters having the ability to get repaired after applying, like for instance, temperature or pH. Or you can also identify other types of smart matters like shell memory or piezoelectric polymer. This is the topic of my talk today. Piezoelectric polymer is based on a coupling effect that you have between an electric response and a mechanical response. And you can have the direct coupling as called the direct piezo effect, enabling the production of electrical charge, or the reverse effect, enabling to generate a mechanical strength when you apply a current. And of course, you can have different types of application based on vibration, strength, motion, and wind. There are different examples that are existing in the case of piezoelectric polymer or any matters based on piezoelectric. You can have the sonar system, the acoustic system, actuator, and sensor. Of course, these different types of application are more or less related with one category of matters, like ceramic, polymer, or crystals. And this type of matters have several advantages, but also some drawbacks. For instance, if you look at the ceramic, they present very high piezoelectricity coefficient, but they are very breakable. In the contrast, you can find crystals that present maybe a very low piezoelectricity coefficient, but they are very stable by comparison with ceramic. So therefore, as a good compromise, we can identify the polymers having a low piezoelectric coefficient by comparison with ceramic, but they confer some flexibility and can be quite easily processed using extrusion technology as a classical manufacturing that you can find in the plastic industry. If you look the best piezoelectric polymer, this is the PVDF. It's a semi-crystalline polymer having a very good ductility with a melting temperature close to 170 degrees and a glass transition close to minus 40 degrees. If you look at the crystalline phase of the PVDS, there are two main phases. The alpha phase, this is the common phase that you obtain after processing PVDF, and this one is non-piezoelectric because all the fluorine are the opposite position from the hydrogen along the backbone of PVDF. To get the best piezoelectric properties, you need to reach the beta phase. This is the beta phase where you can identify the whole fluorine at the same direction, giving the largest dipole moment and giving a value close to 30 pecon per Newton. However, to obtain the beta phase, you need to apply indirect approach like switching, copperization, or blending. The current way to obtain the beta phase can be based on the stretching approach or by copperization. In the case of the stretching, you need to apply from any films, PVDF films, orientation in order to crystallize the PVDF as a polar phase. Or you can carry out a copperization, meaning that you introduce a common monomer inside the backbone of the PVDF, like the TRFE. Of course, this methodology has some drawbacks, like a complex formatting and also the fact that you have to increase the production cost based on the stretching approach, or in the case of the copperization, you can have some physical limitation, particularly the Curie temperature decreasing with the content of the comonomer inside the PVDF chain. So the most promising approach is the blending. When you talk about blending, you have to consider immiscible blend or miscible blend. Most of the polymer blend are immiscible, so they don't have any affinity. But in the case of some immiscible blend, you can have some affinity based on the fact that you have intermolecular interaction. And such driving force can improve the physical properties, especially the PVDF crystallization, in order to obtain the beta phase. To obtain this type of blends, there's two main approaches. The second one, based on the solution that you can make from PVDF and any additive, in this case another polymer, that you solverize in a common solvent, you evaporate to obtain a dry film, or you have a second approach based on extrusion technology. In this case, you start directly from solid particles like PVDF that you add at the upper, you melt all the particles or all the additive, and you obtain from the die different geometry like a tube or a film. And this method is more interesting because they can produce at very low cost because you can carry out in a continuous way. You start directly from polymer pellets without any modification or pre-modification. And of course, you don't have to use any solvent, and this technique is quite industrializable at the end. To develop the PVDF blend, we have selected in this investigation the PMMA because most of the literature have already mentioned that PMMA is miscible and can have a modification, particularly on the melting temperature and the glass transition. The reason that PMMA is very interesting is simple because when you look the micromolecular backbone of PMMA versus the PVDF, you can see the possibility to have a hydrogen bonding between these two moieties, and therefore you can bring some miscibility and you can modify the crystalline phase passing from the alpha to the beta phase. Of course, PMMA is well known, is as we know now as a plexiglass materials, is cheap, commercially available, and can promote the beta phase, not having any impact on the Curie temperature in the contrast to the copolymerization. There are some limitations based on the PMMA PVDF blend as reported by the literature. We can see that from some paper you need at least 20% of PMMA to promote the beta phase, and other papers have reported that when you add PMMA you can reduce the piezoelectric effect of these matters. Of course, there are some lack of understanding about the real effect of the PMMA, particularly on the fact that we don't know what is going on about the effect of the PMMA on the crystallization of PVDF, but also what is the nature of the interface, particularly the amorphous region combining the amorphous part from the PVDF and the amorphous part from the PMMA. And therefore, it was very important in the investigation that we have carried out in the joint PhD to understand the crystallization and also the coupling that you can have when you add PMMA inside this type of. So we have an innovative approach based on the solvent free to understand the influence of the PMMA on the PVDF crystallization. The motivation was based on extrusion technology that is industrially relevant technique. And we carry out the compounding with PVDF and PMMA by melt processing in order to investigate the beta phase. Two post-processing techniques were investigated, the thermocompression as a static approach and a continuous approach based on the calendering technique in order to produce constantly films that you can directly obtain with piezoelectric properties that I will show in a few seconds. To identify the best process in terms of crystallization, we use two techniques to understand: the wax analysis and the infrared analysis based on this blend. And we make a comparison on the films containing a thickness of 60 micron. First of all, in the case of the extrusion thermocompression, the static method, we observe by infrared the appearance of alpha peak and beta peak that is only appearing when you add over 25% of PMMA. However, when you add more than 48% of PMMA, the film is totally amorphous. Very interesting in the case of the extrusion technique, when you apply a calendering step, you can see that the beta phase is appearing after only 5% of PMMA, and the beta phase is the most important phase at 5 and even at 10%. To understand the crystallization behavior of this blend, we use the fast DSC technique in order to apply a cooling and integrate very fast. And using such technique, you can quite easily identify any crystallization event in a function of the cooling rate. So this is the result in the case of neat PVDF when we investigate the cooling rate from -3000 up to -80. You can see from this graph the presence of two peaks, one related with the polar phase, beta phase particularly, and the alpha phase from the other side. And you have a fissure where you can see the both peaks at around -400. When you add 5% of PMMA, you can see that the fissure appearing at early state at -120 degrees, and is even in the case of 10% base PMMA where you can see the fissure appearing at -50. Of course, the results from the fast VSC have also shown that when you add more than 20% of PMMA, you obtain a fully amorphous matter, indicating the absence of any crystallization at the end. So this is a comparison that we wanted to make between a copolymer containing the butyl methacrylate in order to modulate the TG of the PMMA at very low content around 10% and another copolymer based on the methacrylic acid in order to introduce some ionizable group at a very low content around 5%. This is the results that we obtain for a blend containing 5% of this derivative PMMA. You can see the PVDF containing the PMMA containing the methacrylic acid, and the PMMA containing the butyl methacrylic. You can see for the two first examples, no different in terms of crystallization, indicating that we don't have any negative or positive effect by adding methacrylic acid. On the contrary, when you look at the butyl acrylic, you can see a decrease of the cooling rate related to the fissure, indicating that you have a negative effect when you use such copolymer. The fact that we have this negative effect can quite be easily explained by reporting the crystallization peak versus the cooling rate. And you can see that the alpha phase or the beta phase is appearing quite earlier in the case of the PMMA or the PMMA containing the acrylic acid. But in the case of the butyl, we can see a slight decrease of the formation of the beta phase because this type of copolymer is quite immiscible with PVDF. To understand the crystallization behavior that we obtain by fast DSC, we investigate by infrared the copolymer impact, particularly in the case of the neat PVDF as a reference versus the PVDF containing the PMMA and the PMMA containing the methacrylic acid. And we report it at 5 and 10%, and the relatively value obtained based on this graph is reporting in this table, particularly the alpha phase content and the beta phase content. You can see it in the case at 5%, a slight increase more or less of 80% of the beta phase when you pass from the PMMA to the copolymer. So another time you have a positive effect. However, this effect is less pronounced at 10%, and you can also observe a reduction of the beta phase content. This is more related to the fact the copolymer maybe is less miscible with the PVDF by comparison with the PMMA. So after investigating the crystallization behavior, we wanted to know what about the ferroelectrical behavior of this blend. And first of all, we make a comparison in the case of the neat PVDF as obtained by extrusion calendering by reporting the polarization value, particularly the reminiscence polarization value and the coercitive electric field request to get this polarization in the case of neat PVDF. And you can see from the graph that you obtain a very low ferroelectric behavior. When you add 5% of PMMA, you can improve the reminiscent polarization passing from 2 to 4. And also you have a decrease of the coercitive electric field. In other terms, you improve the pooling process using this PMMA. However, when you add 10% of PMMA, you don't modify the coercitive electric field, but you have a decrease of the reminiscent polarization field. In other terms, you don't accumulate so much charge by comparison with the blend containing 5%. And this is particularly true when you add 20% of PMMA, where you observe no any piezo or ferroelectric behavior, indicating that you have more or less a dielectric behavior in this case. And this is the summary based on this value. where we can see that the best results in terms of reminiscent polarization is obtained at 5%, but the ethical field applied is more or less improved when you add more and more PMMA in this system. Of course, we wanted to see what about the coprimer containing the methacrylic acid. And in this case, we make a comparison with 5% of PMMA and 5% of this coprimer. And you can see the value reported. And of course, the reminiscent polarization value is improved in the case of the coprimer, and also the decrease of the causative electric field attesting that you improve the pooling process of the system. And this is based on a dipole density that is provided in the case of this coprimer containing ionizable moieties, but maybe also an improvement of the switching dynamics that is involved when you apply a pooling process, in this case of. Of course, based on that, we're reporting the coefficient, particularly the D33 on this system, and based on the remnant polarization. And you can see that, of course, when you add a very large fraction of PMMA, you have more or less no polarization and, of course, a very low coefficient. But this is improved in the case of the samples containing 5%, particularly in the case of the coprimer containing the methacrylic acid at the end. And this is the best result that we obtain without any annealing afterwards, indicating that our approach is quite solid by comparison with other approaches based on the stretching or based on the copolymization. So as a conclusion, starting from a commercial grade of PVDF as provided by ACMA, and by applying an extrusion calendering process in order to promote the beta phase, we were able to achieve such results by the fact that you have positive or additional hydrogen bonding that can promote the beta phase as shown by crystallization investigation. Of course, the ferroelectric study is also improved, particularly in the case of the PMMA and the coprimer containing the methacrylate, and that has a very positive effect on the coefficient, the D33, obtaining a value of 11 without any annealing post-processing afterwards. As a perspective, we would like to improve the ferroelectric properties of this blend using different scenarios. The first one based on the modulation of the mechanical properties, and the second one based on the modulation of the intrinsic conductivity of this blend. For instance, in the case of the mechanical properties, we can modulate the TG by using another coprimer, or we can add some nanoconductive particles in order to improve the intrinsic conductivity of this blend. Of course, there are different other perspectives based on the choice of the additive, the extension of the dielectric or developing a prototype that can be transposable to real application. As a final word, I would like to acknowledge all the people that were involved in this work, particularly Dr. Alexandre Deneve during the PhD degree in a collaboration with IMT Lille-Douai, particularly with Dr. Cedric Samuel. Of course, we collaborate with different research groups for the crystallization like UMED, or for understanding the ferroelectric behavior with Madrid, and also the sponsorship from BioAv as mentioned here. Finally, I would like to thank for your kind attention. In the case that you have any comment or question, you can contact me on this email address as mentioned at the bottom of the slide. And again, thank you for your kind attention. Thanks.